Hello, I'm Ezra. This is AP Calculus BC Review, Unit 9, Parametric and Polar Equations. In this unit, we talk about vector functions. We look at slope, speed, and distance with parametric equations. We look at polar equations, as well as converting polar to Cartesian coordinates. We look at the slope of polar functions, and then finally, we look at the area under and between polar curves. So let's begin. So, what is a vector function, or what is also called is a vector valued function? So, this is essentially a function, we're going to say r of t, which is made up of parametric equations. So, a parametric equation is essentially a set of equations where your x value and your y value depend on time. So what does this mean in relation to normal equations? Well, normally you have f of x or y equals x, and that means that the height of the function depends on the x value. In parametric equations, both the height of the function y of t and the length of the function, or what position it is on the x-axis, both of these depend on the variable time. So what you can end up having is a function that looks really wonky, that looks anything like this. You can have a normal looking function, it could look like this, but for instance, if you have some sort of oscillating function as your x, it can end up going back and forth in between two x values. So a vector valued function is just a function made up of two parametric equations. So you write it with this little angular bracket right here, and you just write it as x of t, y of t. So this is a position function because we have the position of x and then the position of y, which depend on time. Now, if we wanted this to be a velocity function, we could say that it is x prime of t, y prime of t, because now x prime of t is the derivative of x, and we know that the derivative of position is velocity. So derivative of x position, derivative of y position, this makes up our velocity vector function. Another way that this velocity function can be written is dx over dt dy over dt, which is more often how you'll see it written. And then we can also take this a step further, have our acceleration function, which would be x double prime of t, y double prime of t, or again, d squared x over dt squared, d squared y over dt squared. So these are kind of our rules for vector functions. It's always going to be position, velocity, and speed. The position function is made up of two position parametric functions. Velocity is made up of the derivatives of those, and then acceleration is the double derivatives of those. So if I were to give you some sort of function, I said x of t equals 8t minus 4, and then I said y of t equals e to the 0.5t, and I said that s of t is my vector valued function, and it was x of t, y of t. If I said to find the velocity function, v of t, all you would do is take the derivative of this function and then put it in place of your x prime of t, and then derivative of this function, and then that takes the place of the y prime of t. So this would be our velocity function. And if you wanted to find the velocity vector at t equals 0, for example, the velocity vector at t equals 0 would just be v of 0, which here would be 8, and then 1/2 e to the 0, because we plugged the 0 into here, and then that's just going to be 8, 1/2. So, now, you can also find the slope of a parametric function. So like I said before, if you have some sort of parametric graph like this, what would be the slope at, let's say, this point right here? How would you find that? And I'm going to say that this is t equals 2. Well, you would need to find dy dx, because remember, this parametric function is not graphed over time, it's graphed over y and x, but the y and x depend on time. So this slope is still going to be a slope in terms of y and x. So this is a formula you need to memorize. The slope, dy over dx, of the graph equals dy over dt over dx over dt. Or in other words, y prime of t over x prime of t. So this is one of the essential formulas you need to memorize. Now we're going to go over a full set of problems after we're done with the parametric section of this. So the next formula you need to remember is the speed of the function. So what that means is, if you have some sort of velocity function, then what would be like the net speed of its movement? Not the velocity, because velocity can be positive or negative. Speed. We want exactly how fast it's going when you take into account both the movement of x and the movement of y. So that is going to be another formula. So speed equals the square root dx over dt squared plus dy over dt squared. So if you wanted to find the speed at a certain time, first you have to plug your functions into these dx dt and dy dt, and then you plug your number in to find the speed at a certain point. There's another equation. There's actually two more equations you need to remember. So d squared y over dx squared. This is the so-called concavity of the parametric function. This also has a formula, and it's not just taking the derivative of this. It is, first of all, taking the derivative of it, dy over dx, and then dividing it by dx over dt again. So what that means is, if I go over here, if I have some sort of function, I say dy over dx equals t squared minus 2t. And then I said dx over dt was t minus 1. That would mean that d squared y over dx squared is the derivative of this dy over dx, which is going to be 2t minus 2, and then I divide it by my dx over dt, t minus 1, and then this ends up just being 2. So that's an example problem of that. Finally, and I know this is a lot of equations, but the distance that the particle travels, I'm just going to denote that as d to save space. So this is the integral from the first time to the second time of speed. Or what you should really think of it as is just the formula integral of dx over dt squared plus dy over dt squared. And why is it the integral of speed? Well, if you think about it, the integral of a velocity function is the position. So the integral of the absolute value of the velocity is going to be the total position, the total distance that you traveled over that time interval. So these are your 4 core formulas. I'm going to give you a second to look at it and keep it in your brain before we do a problem together, a sample problem. So, using these 4 equations, I will give you dx over dt. I will give you as the square root of t plus 2 over e to the t. I will give you dy over dt as sine squared t. So, the first part, find the slope at t equals 2. So when it says slope, you have to think dy dx. So let's find our dy dx at t equals 2. We're going to put dy dt over dx dt to find our slope. So we're going to have sine squared of 2 over square root t, or 2 plus 2, which I'm going to say is just square root of 4 or 2. So I'm going to just replace this, or not, I guess. I'm just going to replace this with 2 over e squared. So really, this equals e squared sine squared of 2 over 2. So if you didn't understand how I got that, I took my dy over dt and put it on top and plugged in 2. And then I took my dx dt, put it on bottom, plugged in 2. So the slope, dy over dx, and then you can put this like kind of bracket thing at t equals 2, is going to be this. Okay. Next part of the problem, find the speed at t equals 4. Alright, so let's plug in our speed equation. Dx over dt squared plus dy over dt squared. Okay. Dx over dt is our square root 2 plus 2, so I'm going to square root 4, or 2 over e squared. And then our dy dt is going to be sine squared of 2. So this is a question you need a calculator for, and I'm not going to calculate. I'm going to leave it like this. But on the actual AP test, you need to put this in decimal form, just to be clear that you know what you're talking about. This should be in decimal form, otherwise they could take a point off. So this is our speed at t equals 4. Okay. Third part, find the acceleration vector at t equals 4. Okay. So our velocity vector, we know, is dx over dt, comma, dy over dt. Well, we have dx over dt, and we have dy over dt. So that would mean, erasing this, our velocity vector is square root t plus 2 over e to the t, comma, sine squared of t. I just realized something with the previous problem. This should be at t equals 4. So it should actually be square root 6, e to the 4, and then sine squared of 4. Anyways, sorry for that mix-up. This is our velocity vector. Okay, and now what we know is our acceleration vector is just the derivative of our velocity vector. So let's take this derivative first, down here. So you take the derivative with respect to t, nothing fancy. So the derivative, we're going to use the quotient rule. E to the t times the derivative of t plus 2 is going to be 1 over 2 square root t plus 2 minus e to the t square root t plus 2 over e to the 2t. Alright, this long equation is our first part of our acceleration vector. Second part is just the derivative of sine squared t, which is 2 cosine t sine t. Okay. And then if we want to find the acceleration vector at t equals 4, it will be a of 4, which will equal e to the 4th. And then I'm going to take these two together. So I'm going to have 1 over 2 root 6 minus root 6 over e to the 8th, comma, 2 cosine 4 sine 4. And then this is our final answer for our acceleration vector at t equals 4. Long answer. And again, you would want to simplify this and this in your calculator for the actual AP test answer. Finally, it is asking for the distance between t equals 2 and t equals 4. So we are just going to integrate the speed from 2 to 4. Square root of dx dt squared. So this time, we don't want to plug in our t equals 4 like we did up here. We want the functions because we're integrating. Over e to the t squared plus sine squared of t squared dt. And now you could plug all of this into a calculator and get your answer for distance. So that is basically the whole of parametric equations condensed into this one problem. We went over the 3 of the major equations. We didn't go over the double derivative, but again, that is just another formula you memorize. And these are the main things that you will be tested on the test. The double derivative does not always show up. These 3 things always will. These 4 things. Distance, vectors, speed, and slope always show up. Now we're going to talk about polar graphs. So, a polar graph is different from a normal, what we call Cartesian graph, not because its x and y depend on time, but because it doesn't think about x and y. It thinks about radius, which is just the distance from the center, from the origin. So, you will have r equals something, some function involving theta. And this just means that the distance from the center depends on the angle. So over here, the distance can be 1, but then over here, the distance can be less than 1, and then it can go all the way over, and then come back, and then do some sort of cool-looking shape. So, you can find Cartesian coordinates from a polar graph too. You can convert them by doing the x-coordinate is r times cosine theta, and then the y-coordinate is r times sine theta. So, if you have a function like r equals theta, which is going to look like a spiral, right? And you wanted this in just normal function coordinates, you would just do the x-coordinate is theta cosine theta. and then the y coordinate is theta sine theta. So this is kind of like parametric equations, because you have an x and a y, but instead of depending on time, they depend on theta. So let's look at an example function. We're going to have 1 plus sine theta, which looks something like this. A little bit more symmetric than what I drew, but yeah. So here you can find, this is our 1 plus sine theta function, or r equals, I should say. So we can work with this graph in many ways. The first of which being, again, you can find the slope of a certain area, or a certain point on the graph, with respect to y and x. dy over dx. Now again, another formula. This time, it is almost identical to the parametric formula. dy over dx is dy over d theta over dx over d theta. Except to find this, it's another extra step, because dy over d theta, we have r. How do we get this to be y and theta? Well, y is r sine theta. So in this case, r being 1 plus sine theta, you have y equals 1 plus sine theta, which is the same thing as sine theta plus sine squared theta. And now, if you take the derivative of this, you will get your dy over d theta, and you can put it up here. Same principle for x. X here is 1 plus sine theta times cosine theta, meaning that x is cosine theta plus sine theta cosine theta. And then if you take the derivative of this and put it on the bottom, you will get your dy over dx. Now this is maybe the most tedious thing in the entirety of not just polar and parametric equations, but literally all of calculus. This is so incredibly tedious. And it's not 100%. You're going to get a polar slope question where you have to do dy over dx equals dy d theta over dx d theta. But knowing how to do it is important, because it can very easily show up and then take you way too long on a question. So knowing how to do it and just getting quick with it is important. So you can also find the area under these. Now with parametric equations, it's quite difficult to really find the area, because every parametric equation is quite different. Here, you can find the area, but the thing to note is that unlike a normal function, like this, which you find the area by going from the function and going straight down to the x-axis, like that, a polar function, remember, comes out of the origin. You have your radius that comes out of the origin. So when you take the integral, when you find the area of it using the formula I'm about to give you, it comes out like this, which for a function like this does not matter because it will give you the same thing, but I will show you when it does matter after this function. So I'm going to redraw it because I drew it quite poorly. That looks much better. Okay, so how would you find the area inside of this entire curve? It's a really weird curve. Well, it is, you guessed it, another formula. 1/2 integral from the first theta to the second theta of r squared d theta. So this is r equals 1 plus sine theta. And polar graphs are usually over 0 to 2 pi, unless stated otherwise. Sometimes it's only over 0 to pi, or 0 to pi over 2, but usually assume that it is over 0 to 2 pi. You want to find the area over this whole region. All you have to do is integrate 1/2 from theta 1, which is 0, and theta 2, which is 2 pi. 0 to 2 pi gives the entire radius of r squared. So 1 plus sine squared, or sine theta, everything squared, d theta. So do not make the mistake of squaring the individual parts. This goes into parentheses, and then you square the whole thing right here. So this would give you the area of this function. Now, what if you have a function that interferes with how area is found, which is, coming out of the curve? Well, there are definitely functions like that. Here is one. I don't know why I just started creating a circle. But this is 1 plus 2 cosine theta. R equals. So, what would this look like when you try taking the area? Well, the issue is it will overlap twice over this. So, when you start here, this is fine, right? As of now, there's no issues. But once you get to this point right here, it will start going like this, and then, I'm going to write with the blue, overlap over here, and then it will continue down, and then overlap over here. So, you essentially find the area of the whole shape, plus it doubly overlaps over this inner loop right here. So, if you wanted to figure out what the area of the shape was, you would need to get rid of that inner overlap. So how do you do that? Well, first, you have to find this right here. Where does it intersect? Well, you can use a calculator for that, but it intersects at theta equals 2 pi over 3 and theta equals 4 pi over 3. So if you want to find the area of this whole shape, first, you're going to want to take just the area of the whole shape of r squared, so 1 plus 2 cosine theta squared d theta. All right, and then here we're going to subtract the integral of 1/2, again, using our polar formula, 1/2 2 pi over 3 to 4 pi over 3 of 1 plus 2 cosine theta squared d theta. This right here will give our area of the function, because it takes the area of the whole thing and then subtracts the extra inner loop that we added. Alright, so when you have a function, normally you can just use the formula once, but occasionally you'll have something like this where you need to account for this extra overlap. So always remember, polar area comes from the origin, not from the x-axis to the y component of the graph. Finally, we can find the area between curves. So here, if you want to find the area between these two curves, you take the area under the top curve and then subtract the area under the bottom curve. In polar, it is sort of a similar scenario. So, let's say we have a graph. I'm going to say it's from 0 to pi instead of 0 to 2 pi. So, I'm going to have a semicircle. And this semicircle's r equals 1/2. And then I'm going to have this weird looking curve, which I'm defining as 2 sine squared theta equals r. Okay, I can't select it, but this is r. So, if I said to find the area that is inside this graph, but outside this graph, that would mean you find the area in here, but above this graph. So like this is like the bounding line. So I will give you your intersection points as well. This is theta equals 5, or theta equals pi over 6. And this one is theta equals 5 pi over 6. So think about from the origin where this is going to come out from. If you want to find the area in this section, what would you have to do? It is sort of like what I said before with the two curves. You're going to have to subtract one from the other. So what you have to do is imagine taking the area from pi over 6 to 5 pi over 6 of this curve right here. That would look like you're taking it here, 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 and then all of this stuff, and then here, here, here. And then, if you wanted to take the area of this semicircle, r equals 1/2, from pi over 6 to 5 pi over 6, you would just take the stuff here as well. So, what you might be thinking right now, can't you just subtract this guy's area between these 2 points, or these two intersections, from this guy's area between these two intersections? And that is exactly correct. So what I mean is, you have the area 1/2 integral pi over 6, 5 pi over 6. Okay, and then you have r squared. So we're going to have 2 sine squared theta squared d theta. Okay, and now we're going to subtract the integral from pi over 6 to 5 pi over 6 of 1/2 squared d theta. Because remember, r equals 1/2 is technically a polar equation. It just means that the radius is always at 1/2. So it's essentially a circle with radius of 1/2. So this is an r, just like this is an r. So we have our inner part here, which is the area right here, getting subtracted by all of this area, and then this will net the area in red right here, the area that is inside of the graph of 2 sine squared theta, but outside the graph of r equals 1/2. So, the takeaways from this unit. Parametric equations, you will always have on the BC test one parametric / polar FRQ. A full FRQ dedicated to this unit. So whether it's an entirely parametric based FRQ, or an entirely polar based FRQ, or you have a polar and parametric hybrid, you will have this on the test. So know how to work with parametric equations. X of t, x prime of t, dot dot dot, y of t, all those. Know the formulas. These formulas will all be tested in some shape or form, whether it's on the FRQ or whether it's on the MCQ. You will be tested on speed, distance, and slope. Occasionally, you'll be tested on d squared y over dx squared, but these three, 100% you will be tested on. So go back in the video, re-watch it, and memorize those formulas. Okay, now you have polar functions. So understand that polar can go into Cartesian coordinates. So x equals r cosine theta, y equals r sine theta. And then you need to know this formula. I mean, 100% you need to know this formula for polar area. And then understand where the area comes from. Which is the origin. So you must understand that the area is coming from the origin out towards the radius of the function. Finally, the area between polar curves. You can do outside minus inside. Or if you want to describe it as top minus bottom, overlap, or total minus overlap, however you want to describe it. Knowing that you can take the area between polar curves just by subtracting one thing from the other, figure out how to do it, because there's more than one way to find it for many of these functions. Just whatever mishmash of different ideas you can add. If you want to add 4 different integrals together and that gives you the right answer, I mean, go ahead, it gives you the right answer. The FRQs are not going to grade you for having the perfect, most simplified integral. It's not going to test you for having the most complex understanding of the topic. It's going to test you on if you can get it right. Can your logical reasoning get the question right, however you want to do it? So that is Unit 9, Parametric and Polar Equations. Thanks for watching.